Okay, Lab 4 consists of 4 physlets from Chapter 3, Projectile Motion Problems, taking from Compadre Physlets. So here we are on problem 3.7. If we play the animation, we see the projectile, and it leaves a track of images as it goes, and then finally moves off screen and stops. So we're asked to find what we're able to observe is the position and time of the projectile throughout its path. And we have this small stepping function. So if you see, if I start with the double forward arrow, it moves it ahead 0.05 seconds. And you see it leaves behind a series of images, but the images happen only every 0.3 seconds. So we can actually get the position of the thing every 0.05 seconds. And in order for a video to take an image every 20th of a second, it needs to take 20 pictures or 20 frames per second. So that's the first part of the problem. And what we want to do is we want to find out what the launch velocity is and what the velocity is at the peak of its path. To get that information, we can take position and time measurements using the cursor and the clock. And we have our 4 kinematics equations from the top of column 2 from the equation sheet that we can use to also do calculations to find answers to those questions. So use your cursor to get the position of the top of the ball at the center. That will give you the X position. And to get the Y position, you'll have to subtract the radius of the ball, and you can get that later when the ball is on the screen. You can measure its diameter and get its radius, and that way you can get the start position of the ball without actually seeing it. And then remembering that the X component doesn't change throughout the flight, right? It's only the Y component that changes. I would launch the ball and have it come back to the position it's at the other side. So across the peak, and now I want to stop it before it goes below the horizon and get it back to that position where it was at 2 units from 0, the top of the ball, right? That will be back to where we started at the same height. So I'll do that with the stepping function. And if you measure it, that's the position where it's back at the exact same height from where it left, and that's 4.8 seconds. So now measure the distance that it's traveled in the X direction and divide that distance, get the X velocity, right? Since the acceleration is 0, just take the delta X and the delta T, and that will be the X component of the velocity, which is the same everywhere, right? It's going to be the same at every point along the path because AX for projectiles equals 0. And then to get the Y component, we could do that a couple ways. So one way is to use equation 1, noticing that the Vy initial is equal to negative Vy final. So they have the same, because they're at the same height, they'll have the same velocity, only one will be negative. And that way we can find the initial velocity. Try that. Okay, a little messy, but here it is. Vy final equals Vi initial plus Ayt. Remember, Vy final is negative Vy initial. The Vy final is actually negative, but if we negate the Vy final, we get Vy initial. And then, so we get negative 2 Vy initial equals At, or Vy initial equals negative Ayt over 2. So negative A is a positive number, 9.8 meters per second squared times 4.8 seconds divided by 2, and this is the value we get. Let me show you another way of getting it. Use equation 3 from the kinematics equation, noting that delta y equals 0, right? Because you start at the same y and you end at the same y. Since that's 0, you can divide by t, and you get the same result we just got. Vy initial equals 1/2. Remember, we divided through by t, so that goes away, and that becomes 1/2 Ayt, the exact same thing we got from the other equation. So there we go. There's actually a third way you could measure the height and find Vy initial over the half cycle, where the y component at the peak is 0. So Vy final would be 0. You could find Vy initial. Okay, the velocity at the peak is just the x component, right? When you're at the peak of the trajectory, the y component for an instant goes to 0, and the velocity is only the x component. And remember, we found the x component by using delta x, delta t in the beginning. All right, let's move on to the next one. Problem 3.8. There are 3 animations where we want to hit the falling apple with the projectile, and we aim the thing above, below, or directly at the apple, and we release the projectile at the instant the apple releases. And if you play the animation, you'll see in every case the projectile hits the apple, and only one of them is correct. And so the way we'll identify which one is correct is which one follows the rules of projectile motion. And the falling ball is a projectile, and the launched projectile is a projectile. And you can measure the positions of these things at different times, at the peak, at the collision, at the beginning. And of course, you always put your cursor dead center on the object when you get its position. And what you'll see is that in every case, the red ball falls with an acceleration equal to negative 9.8. So there's nothing wrong with the ball. That does the same thing. But when you do the measurements and the calculations, you'll see only one of the projectiles has a negative acceleration in the y direction. That's the correct value. So I think that's all I'm going to say about this one. Let's go to the next one. I do have one hint, actually, for getting a good reading of the peak value of the projectile, since it's a little bit, I'll show you what I mean. Let's play it out, and let me stop it. So luckily we have this step function, and you see it's, so what you want to do is you want to take it to the point where it's definitely going down. Okay, you see it definitely stepped down there. So if we go back to here, you see it went up. That's 0.98 seconds. And if you measure the position, you see it's pretty flat at the top. So you get the end at which it's definitely going down, and then walk back to the end where it definitely goes down again. You see all that is pretty flat. I think that's definitely stepped down. That's certainly stepped down. So somewhere about here, so that's 0.78 and 0.98, right? The time, it went from 0.78 to 0.98. So you could pick the time of maximum height as the middle of those two, 0.88. And if you get the y value isn't going to change much because it's pretty flat, but there's going to be a big change in x value from about -8. Wait. Yeah, somewhere around the x value, somewhere around 8, all the way to -4. So if you pick the middle of that, you would get -6 for the x value. Anyway, don't trust the measurements that I just took because I'm doing them on this screen that isn't very good. So, but you get the idea. If there's a wide interval, find the obvious ends of the interval and then take the peak values as being at the center of the interval of all possible, or the range of possible values that could be at the peak. Number 9. So in this one you don't have a clock. You have the initial velocity is given, and you can read position with your cursor. And the line represents the initial direction of the velocity. So to get the components of this velocity, you need to know this angle. And so use the grid lines and your coordinate measuring thing to find the slope of this line, and do it very carefully because it's expecting a good precision. So be very careful in your measurement of this angle. Once you have the angle, you can use sine and cosine to get the components, and once you have the components, you can use your kinematics equations to calculate the maximum height, because if you play the thing, if you play it, you'll see that it goes off the screen. And so you can't measure the height. But you can measure how far downrange it goes, and from the initial velocities you can calculate the height and answer the other questions asked. Want some hints? This is equation 1, and if you go from the bottom to the high point, Vy final will be 0. Vy initial you got from V initial sine theta. Once you measure theta, the acceleration is a -9.80 meters per second. And so you can get the time it takes to get to the peak. And once you have the time, you could get the height. But even without the time, right, you have equation 4, which says Vy final squared equals Vy initial squared plus 2ay delta y. And if you go from the bottom to the peak, Vy final is 0, Vy initial is known, ay is a -9.80, and so you could calculate delta y that way. Once you have the time, you can also get it, or once you have this, you could get the time. So just use your kinematics equations wisely, and you'll get the answers to all those questions. Number 10, you can set the velocity of the car and the angle that the projectile is launched at. So if we run the simulation, we see the Lamborghini comes by. As soon as it gets to the center, the projectile is launched. And you see how you can see, watch the ball in the Lamborghini. You see the ball's getting ahead of the Lamborghini. And so we need to do what? Either a steeper angle. Actually, there were two angles that it would hit, right? If you go at a lower angle, it might hit. And if you go at a higher angle, it might hit. I didn't draw that very well, but something like that. It turns out that 45 degrees is the maximum range you get on a projectile. So there's possible two answers for these problems. But anyway, so at 20 meters per second, obviously we have to set the angle higher or lower. How do we determine what that angle is? We need to know the velocity of the Lamborghini. And then what do we want? We want the x component of the projectile velocity to be exactly equal to the Lamborghini velocity, right? Because the x component won't change and the ball will just go up and down while following the Lamborghini. So how do we get the velocity of the Lamborghini? Let's measure it. So you might as well measure from the center of that yellow box and get two positions, and that way you can get a distance and a time, and you can do that for the whole trip. You can do it for half the trip. You can do it for any interval, and you might check 2 or 3 intervals just to make sure that you get the same velocity in each case. And actually it's better to get several measurements and take an average so you have a good estimate of the Lamborghini velocity. And then you want to get your Vx equal to the projectile cosine theta, like in this case 20 meters per second, and that has to be equal to the Lamborghini velocity that you measured. That's why you want to measure that well. And so the angle you want is just going to be V Lamborghini over V projectile inverse cosine. And that should work for to get the angle for any velocity of the projectile. The Lamborghini, of course, is fixed. And finally, the table of contents, where at the time in the video when I start solving each of the 4 lab problems.